Alright, so we first test our code to validate that it's working. We just use the coordinates we use for testing first. Alright, so our generated map is here. I can show that there's a kind of very clear path here. And to make sure we didn't really hard code it, we just like do another round of with another set of coordinates. I probably use the same starting position here. Yeah, but instead of the previous one, let's just do like 46 maybe 40. 46, 6 here. Alright, so the path generated is here. You can see there's a different different path plotted here, and our buffer is kind of like something here. You can see that those are circular buffers because we use a circular mask to somehow do the buffering. So I'll explain our general logic of the code first. Like we have we construct our code such that it's very modular. Each module have a separate file for it, and we just like our main function is just this long. What we basically do is just like call the path planning function, which I'll first do the mapping first. Mapping first, you get the original map and get the buffer map. What we do here is basically we have an original map. We threshold it to like to binary map, and then we somehow use a kind of like a very simple whether it's black or not to get a like to get a map of true and false, and basically if it's not the black, it will be true, and then all the others will be false, so that all the obstacles will be true. And then later we also construct a mask. In this mask, it's kind of like a circular mask with the radius being the radius of the buffer our selected buffer radius. And what we do is basically just like shift all, apply the mask by shift all to the all the grids here to get our final buffered buffer map. And for our planning part, we use the A-star algorithm, but instead of like just using the traditional one with constant cost plotted in the map, we just use the dynamic programming because like we want to account for the turning penalty for those robot, meaning like we want to make it turn as little as possible. So what our cost function does is like instead of like a base cost here, we add another turning penalty, which is calculated based on your previous direction carried in the ASI algorithm and your current direction get from your neighboring basically, and then you got your like you turn how many times of 45 degrees, and for each time you turn you get a 0.5 like a 0.5 penalty for that. So in this case, we have a dynamic programming of it, and then we actually just somehow make it to that it turns as at the least time as possible. And for the A-star, we already covered the cost function, and what it takes is like the graph, of course, and then the buffer graph here, starting and end position, and then the starting direction. And for this A-star algorithm, the key data here is like basically a priority queue here, implemented by the heap push and like heap hop stuff. And then we also have a confront to reconstruct the path when the A-star, the main part of the A-star is just finished. We also have like 3 key parameters here. The G cost is basically just a dictionary keeping track of like how much cost you take to how much cost you at least take from the starting position to your current position. And in addition to that, we also have a fcost. Basically, is addition is like gcost plus a heuristic function, which calculates how long it takes from your current position to your end position. So actually, with the fcost function, we got like kind of like an overall score of how well your current position is. So we give another name of F score, which is used to somehow evaluate whether we should prioritize this or this coordinate or other coordinates in the priority queue. So for the neighboring part, we actually used 8 direction neighboring, and in addition to the current position and current row and current column, we also keep track of the previous current orientation into the like dictionary into the dictionary, or sorry, into the priority queue. And this dr and dc, when doing the neighboring, give us the current direction, and we keep track of the previous orientation. With those 2 orientations, we are able to get the turning penalties we just mentioned before in the cost function. And all the others, which was mentioned, is just basically here it updates like all the gcosts and come from used to reconstruct the pass F score, we mentioned it before, and also the priority queue. And there's kind of like a reconstruct function being here, and they just like give it to and then a star algorithm basically just ends here, and then the following is the odometry, which is used to somehow make the robot follow our paths. And also what was mentioning is we generate waypoints for our trajectory, so that we actually get rid of the middle points between a kind of like direction between a straight line. So we only have the starting and ending point in our waypoint in our final waypoints. And for odometry, our code used the pure pursuit, and it's still tuning, so like we don't really have the time to somehow illustrate this. And but I think it is enough for the check-in video for Monday. And